So in the last class, we were talking about image processing applications and in how in image processing applications, we usually apply a filter, a convolution filter. So here in this picture, you can see there is an image and we are keeping a 3x3 convolution filter at a particular position. And then the corresponding, we take a dot product of this window with the corresponding pixels from the image. And that will result in the pixel that you are seeing on the right hand side. And you take this window and you start keeping it, you just move this window around the source image. And as you move the window around the source image, you render the output image. The coefficients, depending upon what kind of transformation you would like to do, the pixel, the filter coefficients are chosen accordingly. And in deep neural networks, you kind of extend this idea, because those of you who are exposed to deep neural networks, you will see that we apply different kinds of filters to an input image or an input volume, and we render an output volume. And different filters will kind of capture different properties about the source image or the source input volume. And we have seen how this thing kind of works. In order to implement this logic in hardware, we will. So if you, the whole source image, we don't need to store on the FPGA memory, on the DRAM. So what we do is, in any image processing application, pretty much in all image processing applications, we stream the image from the DDR memory, and we store few rows of the image on the FPGA DRAM. Either you use DRAM or some other kind of memory on the FPGA we use. So this is what is called as a line buffer. So what happens is, here if you see, F is the stencil operation. So there is a stencil operation you want to apply. So what happens is, so here, so let's say if this is the stencil, I'm representing this node as application of a stencil F, and input is coming, it reads this stage, this hardware module F reads the pixels from the input stream. And once the line buffer contains sufficient number of pixels so that it can start applying the filter, like for example, here, it has to wait until the first, in the case of a 3x3 filter, the first 2 rows should be available, and then the first 3 pixels from the first 3 columns in the third row should also be there, so that the computation can start happening. So as pixels are streamed inside, so you keep moving this red window this way, okay, and you generate the output pixels. So in a steady state, what happens is, for example, here you can see the line buffer contains this this is the data that is present in the line buffer on the FPGA, and then you apply this filter here, and you generate this output pixel. So this is how the computation happens. So there are two important things that I wanted you to remember from the last class. One is this model of computation. It has two important components in it. One is it's called as a data flow model of computation, and this is also it's also called as a streaming model of computation. So there is both data flow and streaming are different. Okay, so why is it data flow? The module F, the hardware module F, which performs the stencil operations. So it has an input Q, it has an input FIFO. So this is the input FIFO. So it keeps waiting for sufficient data to be accumulated in the input FIFO. Okay, that is the, and then it generates the pixels in an output FIFO. So as soon as sufficient data is available in this FIFO, this particular module fires. Okay, this module fires, and then it does the computation. So synchronization is automatic. If the FIFO doesn't have sufficient data, or if the FIFO is empty, then F waits. And why is this a streaming model of computation? Because we are streaming in the image from DDR memory onto the FPGA fabric, and we are doing computations there. So this is these two keywords I would like you to remember, because they are very important design principles in coming up with architectures to solve new problems.
Sir, you're not audible.
Sir, you got muted a couple of time while ago.
Hey, sorry guys, there is some problem. Yeah, I'm back. I'm not talking, but I got muted and my mouse wasn't working. Anyway, so I'm back. Yeah. So let's hope we wouldn't have any issues now. Okay. So here, so this data, depending upon the application, you need to see whether this particular combination of this architectural approach suits you. And yeah, so let's clear let's revisit the code example that we were seeing last time. So in this code example, so this filter 2D kernel is the core function which gets synthesized into hardware. And as you can see, this contains 4 stages of computation, 4 stages of computation. And on line 215, you can see the pragma, data flow pragma. You can see this data flow pragma. And then you can see on line 218, 219, 220, 221, all these streams, coefficient stream, pixel stream, window stream, output stream, so on and so forth. So the picture, the logical picture for this, if you see, this picture, so there is this, I will use, there is this stage RM that is read from memory. And this read from memory stage, it reads data. This is your DDR memory. So this is your DDR memory. This memory is not on the host. This is on the FPGA. Okay, it reads it from memory, and then what it does is there is this window 2D stage, and there is a FIFO or a stream which connects these 2 stages. And these 2 stages, like this is, I think it's called as pixel stream. This in this parlance, the variable names that are used, this is P_X, shorthand for pixel stream. And this Windows 2D module, it feeds in data to filter 2D module, and there is and it uses a FIFO to feed data, to feed Windows to filter 2D module. These windows are, remember these streams, these FIFOs, no, they are templates. So they can take arbitrary data types. So you can exploit it to your benefit when you are designing your system. And this filter 2D, once this is where the actual computation is happening. This is the actual computation is happening. And then it outputs the data into output stream. This is O_S, this output stream, FIFO. And then there is one more module, write to mem module. This is read module. This is write module. And then this writes to DDR memory. So this is called as an image processing pipeline. Okay. So although in this pipeline, there is only one computation stage, the other stages are reading from memory, window creation, writing to the memory, so on and so forth. There is only one computation in this image processing pipeline. And in fact, this is a linear pipeline. And in today's class, you will see you can, the image processing pipelines generally could be more complex than this pipeline. So speaking of image processing pipelines,
so that filter code, excuse me, sir, that filter code is a built-in function or
no, it is written. It is written. It is. You can see this. We looked at this code. This is the function. Line number 40.
Sorry.
Okay, so. So while so when we think of image processing pipelines, so each stage in the example that we have seen, a stage takes, at a particular stage, we are applying stencil computations. And there are different kinds of stages depending upon what kind of computations are being done there. Like, for example, there could be a stage where we perform point-wise computations. What is a point-wise computation? So here we are taking the RGB channels and then we are kind of mixing them and we are generating a output pixel. So conversion of color image to a grayscale image. Point-wise computation means that the computation depends on a particular pixel, not on the neighborhood of the pixel. That is, if you want to generate, in order to generate this pixel, you need the corresponding pixel. You don't need the neighborhood of this pixel. Since you don't need the neighborhood of this pixel, this is not required. You don't need to maintain line buffers, for example, when you are doing point-wise computations. So point-wise computations are relatively easy to do when compared with stencil computations. And then you can, so stencil computations are over, point-wise computations are over, and then we can do what are called as downsampling applications, operations. So this is an example of a downsampling operation. So like, for example, when we apply a filter with a particular stride 2 means you don't apply it every place, you apply it at alternate places. Then downsampling automatically happens. So downsampling is so what happens when we do downsampling is the stage which is doing downsampling, if it is receiving 100 pixels per second, then it may output 25 pixels per second. So the downstream stages which consume this input, they could be, they might be able to process more pixels, but because there is a kind of funneling happening, so they may be deprived of enough data to do computations at their peak performance. Anyway, so downsampling is one such operation. Similarly, we have upsampling operation. So in image processing pipelines, if you see many image processing pipelines, they have these computations like point-wise computations, which are the simplest, and then stencil, and then downsampling, and then upsampling. And there are different ways of doing upsampling and downsampling. And these stages are put together in some nice way to achieve some end goal. So for example, if you see one example, there is this image processing pipeline called as unsharp mask. In this, unsharp mask, so that the first stage IIN, it's like read from memory stage. And then there is a blurx stage, which is a stencil stage. And then the output of the blurx is a image, and it is streamed. Data is streamed from blurx to blurY. blurY performs so blurY performs again different kind of stencil operation, and sharpen is a point-wise stencil stage, and it has two input. No, it's not a point-wise stencil. It's just a point-wise stage, and it has and it reads two input streams, two FIFOs, and combines them and generates one output stream. And masked is again another point-wise stage, which reads two input streams and generates one output stream. So finally, when you pass an image like what you are seeing on the top right-hand side, and when you pass this image through this or stream this image through this image processing kernel, we see the sharpened image at the bottom. Great. So in terms of the coding logic, the architectural approach is the same. It's a combination of streaming and data flow. Each blurx, blurY, sharpen, mask, they are all data flow stages, and they are all connected to each other via FIFOs. Whenever any of these stages, they have enough input on their FIFOs, they will fire and do the necessary computation. You can see there is a lot of parallel computation. There is an interstage pipeline parallelism. So there is an interstage. If you see in this, there is an interstage pipeline parallelism. And then that is when when computations are happening in blurx, computations are happening in blurY too. And actually within a stage also, we can have a parallelism, intra-stage pipeline parallelism. Like for example, when you are, if you are doing some, what do I say? Applying a stencil operation, there is a lot of parallelism that is available in applying a stencil on a window. Intrastage pipeline or other kinds of parallelism, intrastage pipeline parallelism. And also it is quite possible for us to apply what is called as a channel parallelism. That is, there are, right now we are seeing a, only a gray image, but let's say if you're applying the same operation on the RGB channels, and we can apply, we can process all the channels in parallel too. Okay. So if you go see the code, there is, if you see the code for this, so we will come to domain-specific languages in a bit. But if you see the code here, this is the HLS code associated . So this is the HLS code associated with the unsharp mask pipeline. You can see it's quite a bit of code. The code is not yet over. One thing I want you to keep a note of is this particular on line number 24, you are declaring the data type, data underscore t type as we are passing some interesting parameters here. It is it's a fixed point data type. Its width is 24 and 12 bits are used for
arbitrary precision, sir.
It's arbitrary precision? No, this is fixed point. No?
AP means, I guess it is arbitrary precision.
No, this is not arbitrary. Arbitrary means you can play. It's not like arbitrary. It is like 24 bits are allocated. You can, it is arbitrary in the sense you can make it 36 if you want.
Yes. Okay.
Yeah. So 24, we will talk about fixed point data types in a while, but what we have is we are saying, that we are using 24 pixels to store 24 bits to store a pixel, and 12 bits are used for the integral part and 12 bits are used for the fractional part. And then you can see this is whole bunch of code, because associated with every stage, you need to write a for loop, and so it all looks, although it is you are writing this whole code in C, the code still looks complex. The code still looks complex. And in fact, when you go for bigger pipe, and then so there will be some set of either you can intersperse the directives within the code using pragmas, or you can put the directives in a separate file, and which tell the HLS compiler on how to go about synthesizing the hardware. The point that we are in today's class, there are two important ideas we want to introduce. One is what is called as domain-specific languages, number one. Number two is how we can do precision estimation in order to optimize on the, or data type estimation in order to optimize our designs. So the point here is, even for a relatively simpler program, image processing pipeline, such as the Sunsharp mask, the code, the amount of code that you have to write, and this is non-trivial. Okay, so this have to work hard. So in order to solve this problem, like, yeah, for example, if you look at pyramid blending, so you can see the number of stages that are here. And if you end up writing code for all these things, even if you write structured code, it is going to be pretty complex and hard to understand. All right. So here comes the idea of domain-specific languages. So I'm just using these slides from that we have for the conference. It's compiler construction. So yeah, maybe just so this is a joint work with so Vinamra is our student now. He is in UC Berkeley, and Jiaul, who is a PhD student, and Uday from IISc. So yeah, just to kind of recap, we were presenting this for a non-FPGA audience, and also since we are in the middle of the course, I'll just give a quick recap on why we are doing what we are doing. That is, when we think of both either edge applications or data center applications running on the data center, the important metric that is performance per watt. So we need good performance, and at the same time, it should be energy efficient. And so by this time, the claim is, when we are considering the options that are available, general purpose processors, GPUs, FPGAs, ASICs, as we move from right to left, the programmability and flexibility increases, but performance per watt metric goes down. But as we move towards right, the performance per watt is really good. ASICs are the best, and then FPGAs come next. But ASICs requires large volume for economies of scale to kick in, but FPGAs are all right because the same FPGAs can be used for so many different applications. So still we may be able to get the economies of scale. And they kind of strike a good balance between trade-off between CPUs and ASICs. Don't want to spend much time here, but this particular point is important. So all ECE students, you would have learned this flow. You have a hardware architecture in mind. We have a problem in mind, that is applying, for example, applying convolution on an image. You come up with a hardware architecture and you express that hardware architecture using Verilog or VHDL. And then you do behavioral simulation, synthesis, place and route, bit stream generation, and then finally you go put it on an FPGA. And in this course, what we are trying to do is, we are not working at the Verilog or VHDL level. we are going one level above and we are trying to express our designs using C, C++, OpenCL specification languages. They are programming languages. They are not specification languages per se. But the logic that is expressed in these programming languages, they are along with some other directives provided, they are mapped to Verilog code. That's what happens. The HLS compiler or YT's compiler, V++ compiler, it translates C or OpenCL programs into equivalent Verilog code. So through this process, we are raising the level of abstraction. But what is a bit unsatisfying about it is, as you can see, it's not easy. You know, you're doing the first assignment, you are still struggling. But I hope in due course of time, you will become experts. Substantial effort is required even when you use even when you take HLS approach. So we would like to raise the level of abstraction. So instead of make it more easier for people to generate hardware designs. So as at some time back, I mentioned the Chisel and BlueSpec system Verilog are competing options for HLS C, C++. But if you think about it, even when you want to express when you use higher level abstractions based on C, C++, or OpenCL, or BlueSpec system Verilog, or Chisel, you require a detailed knowledge of hardware. Just because you are writing your stuff in C, C++, it doesn't mean, that you don't need to know anything about hardware. You need to know quite a bit, like how does pipelining work? How does loop unrolling work? How does, how to use DSPs, how to move data from, how to read memory, how to use VRAM. There are so many things that you need to know in order to get good performance. So if you are just a C programmer and don't think that you can just automatically write code in C and things will work out for you. You have to put in good amount of effort. Although these tools are getting better and better, but you still need to have good knowledge. So the idea behind domain-specific languages is to come up with a is to kind of have language constructs which work for restricted space. And we have design compilers which translate these programs into equivalent C, C++ programs or BlueSpec system Verilog programs, or even directly Verilog programs. So that the idea is to completely take you away from the hardware architectural details. It may, in some cases it is possible, in some cases it may not be possible, but that is the wishful thinking. So for example, if you look at this particular image processing pipeline, this is called as Harris corner detection pipeline. So you can see that there are stage IX is a stencil stage, and the stencil that is applied you can see on the right hand side in the table. Stage IY is also a stencil stage. Stage IXX is a point-wise stage where whatever the input pixels that you get, you just square them and you generate the output image. Same is the case with IYY. And IXY, it takes two input streams, one from IX and one from IY, and then it multiplies the corresponding pixels. So that's this. This is what is happening here. So you can see IXY It takes IX and IY and it's, yeah, so just pay attention here. And SXX is a SXX, SXY, SYY. They are all stencil stages. Determinant and trace are pointwise stages. Harris is again a pointwise stage. So this whole HCD pipeline, it consists of some stencil stages and some pointwise stages. I hope you're all with me on this DAG. Yes, no? Can I see some raise of hands or messages on how you're doing? Okay, good. At least some people are following. So if you have to express this HCD algorithm and write a image processing and write HLS code for it straight, while it is possible, it's going to take a good amount of effort in setting up the right data flow structure and get good performance out of it, so on and so forth. So there are domain-specific languages to express image processing pipelines. Like, for example, Halide is very popular domain-specific language using which we can express these pipelines. Similarly, from Stanford, they have Darkroom, and the latest one from Stanford, they have something else. After Darkroom, they have Rigel. After Rigel, they have something else. But Stanford has, is there someone who can tell me what is one particular domain-specific language from Stanford, which is very popular these days? They are pushing for it. I forgot. And then there is polyimage from ISC. We worked with ISC using the polyimage domain-specific language. And now we have our own domain-specific language, which we didn't yet publicly release, but it's based on Scala, and it is really good. And we call it as Flowpix. So, yeah. So the point is, yeah, so now, how do we express this as a domain-specific language? Like, this is the Scala code, which expresses this, the computations that are there in this DAG. So every line here, on line 1, it says on the image apply, the star is the application of a stencil operation. So dy is a stencil, and we are saying, so we obtain the image IY by applying the stencil dy on image, whatever the object that is held by this image variable. Similarly, we get Ix by applying dx stencil on img, and then Ixx is equal to Ix times Ix, so on and so forth. So this whole code, this DAG is almost line to line expressed using in this DSL. You can see how easy the DSL is to write. Very, very powerful. And then what we do is the Flowpix compiler, it takes the DSL program and it generates a hardware design in BlueSpec system Verilog, and there is a BlueSpec compiler which maps it to Verilog code, and then the Verilog code is passed to Xilinx or Intel Altera tools, and finally it is etched on the FPGA fabric. This is the flow that we have, but earlier we were working using polyimage DSL, While Flowpix is based on Scala, Polyimage is based on Python. It's a Python language-based DSL. And there is a Polyimage source-to-source compiler. What it does is it takes the Python DSL and then it can map it to OpenMP code so that C++ code with OpenMP Pragma so that the resulting code can run on multi-core CPUs, or it can generate CUDA programs so that they can run on GPUs, or it can generate C++ code, HLS C++ code so that it can be passed through the Xilinx tools, for example. The interesting thing is when we use DSLs, as you can clearly see, it enhances the programmer productivity. You don't write a loop. So what happens? You have to, if you line number 6, if you write in HLSC, you have to write 3D loop. You have to maintain line buffers, you have to use streams, lots of stuff you have to use. Forget about FPGAs. Even if you want to write it for a multi-core CPU, you still have to write a 2D loop. And if the same operation has to be applied on all the channels, then there is a surrounding loop around it. And just at least this 15 lines of code, each line of code here, it would translate to 10 lines of code minimum. So with 15 lines, you have 150 lines of code at least you have to write. And so programmability is an issue. Second is, when you write your program as a loop, you lose a lot of very interesting information, because when you are applying a pointwise operation or stencil operation, there is a lot of structural information that is present. And when you write a loop, you are just throwing away all the information, and you expect the compiler to reconstruct that information and do through program analysis, through complex program analysis. This is where techniques from polyhedral compilation, etc., also come in. How do we analyze loops? How do we analyze dependencies in the loops? So all these challenges have to be, program analysis challenges have to be solved. But when you write it in this form, we are retaining the structural information. There's a beautiful information that when we, on line number 4, when we say IYY is equal to IY times IY, you are saying we are multiplying two matrices pointwise. Or when you say IYY is equal to IY plus IY, then you are clearly saying that you are adding two matrices. This structural information makes it easy for the compiler to focus on transformations which will improve performance rather than on analysis, rather than on program analysis. So that is the last point. So you make it easy for the compiler. Otherwise it will have to work hard to reconstruct the information that you have thrown away in the process of writing a C program. And focus on transformation rather than on analysis. So this is about DSLs. This is a very hot topic. So those of you who, this could be a research topic for some of you who would like to work in the space of compilers and FPGAs, etc. This is a good topic to look at. So now, we look at a specific optimization called as bit width customization. So in the image processing pipelines that we have looked at, we know that the image is an 8-bit pixel, and you keep applying operations on it. If you write a program for the same on CPUs, we use data types such as float, double, long int, int, etc. So this is the granularity at which the data types are available when we are this is the granularity at which the data types are available on CPUs and GPUs. So you have to work with them. But on the FPGAs, we have a lot of flexibility in the kind of data types that we would like, that we want to use in our design. So you can use float, perhaps double, or you can use what are called as fixed point representations. So fixed point representation is very simple. So let's see. So fixed point representation, it has two parameters, that is a fixed point data type is specified by a tuple alpha comma beta. Like for it's the way we learn stuff in school. It's like something like 12.36 means what is the value of 2? This is 10 power 0. The value of 1 is it has to be multiplied by the place value of 1 here is 10 power 1. So this is 10 power minus 1, 6, 10 power minus 2. And if you are working with binary, so we do the same. So this 2 power 0, 2 power 1, 2 square, 2 power minus 1, 2 power minus 2, so on and so forth. So if we are working with pixels, and we know the stencil operations that we apply and pointwise operations that we apply, they don't require, they are not going to, those values are not going to jump to huge values, because when floating point data types are designed on for CPUs, since they are ASICs, the data types are designed in such a way that we will be able to represent almost at the infinite range, because real number line is infinite. So you want to represent infinite number using finite number of bits, 32 bits in the case of float, and double uses 64. So again, you may use 64 bits, but nevertheless you are mapping an infinite range to a finite space. And they are being done because when you design arithmetic and logic unit in your CPUs or in GPUs, once they are, you have to design for specific data types. Okay, you cannot have arbitrary stuff. So well, in any case, so when you in the case of FPGAs, we have the choice, we have the flexibility to define our own data types, fixed point data types. So if we are able to, instead of using 32 bits, if we are able to use 9 bits to store a value or 10 bits to store a value, the amount of on-chip DRAM memory, using the same amount of on-chip DRAM memory, will be able to store more data. Like for example, instead of using 32 bits, if you are able to use 16 bits or 15 bits, then the memory the effective memory capacity, DRAM capacity, doubles. And the memory bandwidth also increases, right? Because memory bandwidth is a serious constraint. So let's say you are working on a problem which is memory bound. This memory is the bottleneck. And then you figured out, hey, I don't need 32 bits to store this, to store each value of the data. I just need 16 bits. Then suddenly what happens is the memory bottleneck, the bandwidth increases, and memory may no longer be the bottleneck, and compute could become the bottleneck. And in fact, there is a whole lot of research on this in deep learning space, because we want to, in deep learning, when models are trained, they are all based on floating point numbers. But then floating point numbers requires 4 bytes, and computations are expensive, all sorts of problems. So there is a lot of work on how do we compress the model by moving from floating point numbers to fixed point numbers to the extent that we want to represent the weights in a deep neural network using under 8 bits or 12 bits or 16 bits, or in the extreme case, binary neural networks, where weights are represented using just weights can be just either 0 or 1. So this is a very, even in the Xilinx tool, if you see this AI tool, so if you give a model that how do we try to maintain the accuracy of the model while keep on reducing the bit widths required to store bit widths required to give the to process the input, whatever it is, without losing on accuracy, there are many tools that are being built. So again, this is an important area of research. It's very hot area. So because when we are trying to squeeze performance, there are many dimensions in which we have to look for stuff, and looking for bit widths is a very important dimension that we need to consider. And it will have impact on area, DSPs used, flip-flops used, FPGA slices used, power consumed, so on and so forth. So the bit width optimization problem is given this is the problem statement, is given a DSL specification of an image processing pipeline. How do we specify, determine the optimal fixed point data types at each of the computational stages? So in order to understand this, if you look at the Harris corner detection problem, recall this is the pipeline for the Harris corner detection. So for several input images, we took the range of the values. Like for example, all the stages that are coming out of the stage IX, we looked at the range of values, and we are able to figure out that like for example, this is through experimental analysis, of course, 99% of the pixels, they require less than 6 bits to represent. And 100% of the pixels can be represented using 8 bits. Similarly, if you look at like for example, trace stage, and if you see the number of bits occupied by the trace stage, all the 100% of the pixels can be represented using 17 bits. And in fact, maybe 99.999% of the pixels could be represented using 15 bits. And in applications such as image processing, if there are some few pixels are hit because of because we are using 15 bits instead of 17 bits, it is all right in the case of video and image processing algorithms. So this graph shows that how much we overdo when we use floating point numbers in our computations, right? So one thing for sure is if we know that trace stage requires whatever the values produced in the trace stage, they can be represented using only 15 bits, then we can use fixed point arithmetic where integral bits are 15 bits in length. So there are two problems here that we have to solve. One is the alpha. So remember, any fixed point data type, it has two parts. Alpha is the integral part, number of bits required for the integral part, and beta is the number of bits required for the precision. So that beta, if it is equal to 1, that is, if you are using only 1 bit after the binary point, then the values are spaced, the space or the gap between values is 0.5. That is a precision level. But if you are using 2 bits, then the gap between the precision level is 0.225 perhaps, And if you use 3 bits in the precision level, then the gap between, two values, it will be 0.125. So while alpha determines the range of values and beta determines what is the gap between these values. Okay, so like for example, you can have alpha is equal to 1 and beta is equal to 30. If the application demands that that we have to make fine-grained distinction between the values that are being produced in the computational pipeline. So we will just focus first on this alpha determination. So like for example, so in order to determine the alpha, if you know that the values produced by the trace stage, they lie between something like minus 110 to, like maybe let's use minus 110 to 120, maybe let's assume. If all the values produced, or 99.999% of the values produced in the trace stage, they fall in this, then what we can do is, we can be confident that we can use 8 bits to, if you look at this range, that is upper minus lower, it is 230 or something, we can represent all the values in this range using 8 bits. So this estimation of alpha estimation, this is the problem that we are looking at. This alpha estimation turns out to be what is called as a range estimation or interval estimation problem. If you are able to estimate the range, then from that range we can figure out how many integral bits we should be allocating for to store data at a particular stage. Okay, so alpha estimation problem turns into a range estimation problem. And in order to do range estimation, we use, so one simple way of doing range estimation is by using what is called as an interval arithmetic. The idea behind interval arithmetic is very simple. Let's say y is equal to x plus z. Okay. And if we know, so somehow we know that x lies between minus 10 to 30. This is the range of x. And z lies between minus 30 to 100. This is the range of z. Then by looking at the range of x and range of z, we will be able to estimate the range of y. So you just add the lower limits. So the range of y will be minus 40 and 1 plus 130. This is y. So by using the range of x and range of z, we can estimate the range of y. Similarly, for different operations, it is possible for us, by looking at the ranges of the source operands, we can estimate the range of the destination operand. And if we go to the base case, in the case of image processing pipelines, we all the time know that the images are of length 8 bits. All right. So this is the story. This is how we can estimate ranges in image processing pipelines. So let's see how this pans out. So this is the basic idea. This is what we want to do. If you want to go back and see this Harris corner detection, in the Harris corner detection, so we know the range of the pixels here is 0 to 255. If this is the range of the pixels here, and if you pass an input operand of type, if the input operands are of type 0 to 255, and when we apply the stencil operation on a pixel of this, what would be the potential output range we estimate? So like that we propagate, and then so here when you see IXY, so it gets one range here and then it gets another range here. You have to merge these two ranges by applying a multiplication operator to generate an output range. So you start with the source range and you keep pushing these ranges through these different stages in the DAG, and the ranges keeps getting generated on the edges. And we use the range on the output edge, like for example, associated with the IXY, to determine what should be the data width length at the stage IXY. All right. So this is the basic range analysis algorithm. This is the basic range analysis algorithm. So here, while we are working on this problem, actually writing an analysis pass, a range analysis pass like this, an interval analysis pass on this, on a DAG is extremely simple. Like it's like you can code it up in Python in maybe in half an hour. But if you want to do the same range analysis, if given the whole DAG, if it is expressed as a C program, and if you have to do range analysis, it's extremely painful. There are lots of research work there on range analysis of variables in C programs, but it's complex. But once we have the DSL and associated DAG, we can easily construct. Then range analysis is like a half an hour job. Writing a range analysis pass is a half an hour job. In fact, it is so simple, no? From a publication point of view, it looks so trivial, like no contribution is there. Okay, so that's but we are getting this power because we are able to retain the structural information that is there, the computational structural information that is there in the DAG. We are able to retain. Great. But what happens is, this range interval analysis has some problems. Let's see where, yeah. So like, for example, in interval analysis, it will not be able to correlate. Like, for example, if we have an expression such as x is equal to a minus a, and if you know the range of a as, or let's say, yeah, a minus a, this is good. So if x is equal to a minus a, like x is always equal to 0. But if you apply range analysis, interval analysis blindly on this, then what happens is the range turns out to be minus 10 to something like 10 or something like that you will get. Yeah, so this is the range that you get if you apply interval analysis. Because when we do interval analysis, when we move from this expression to these ranges, we are ignoring the source variables and we are just working on the ranges. And because of that, correlations are not captured in interval analysis. So because of that, people apply techniques such as what are called as affine analysis, affine arithmetic analysis. So this affine arithmetic analysis, it will be able to capture the correlations. But the problem is applying affine analysis on image processing DAGs is not quite straightforward. We have to, it is not as straightforward as applying interval analysis on DAGs. So here, so one very, when I looked at it for the first time, so along with my student, we found it super exciting, one interesting idea here. So here, let's say this is the code associated with Sobel filter. Sobel filter is one image processing filter. You can see, there is an image, you take as input an image and you output an image stream. You take an input image stream and you output an output image stream. And then there is line buffer and window buffer, all sorts of things in this code. And the interesting thing I would like you to pay attention is this thing. We are not specifying the type here. It is just written as a TYP. Okay, it is written as TYP. But if you see, This TYP, this can be, so this TYP, this can be a float, this can be a double, this can be an int, or this can be, that fixed point arithmetic data type, which we have seen sometime before. So it can be any one of these data types. And not only this, it can be of type interval. Okay, this can be of type interval. So what happens is when it is of type interval, like if you see here, there is this one particular library like for interval analysis. So if you define TYP as this particular type easyval, then what happens is when computations are you generate from the Polymage source code or the Flowpix source code, you generate the HLS code and you set the type to easyval, and then you run the program in the simulation mode, software simulation mode. And when you run the program in the simulation mode, then what happens is the computations that are happening in the software simulation mode, they are no longer regular pixel operations. They are, interval arithmetic operations are happening. So because of that, by the time we finish the program execution, we know precisely the intervals associated with the different pixels at different stages precisely. And similarly, if you want to do affine arithmetic analysis, you just need to change affine analysis. You just need to change the TYP variable to this particular type on line 4. And then you just run the program, the generated HLS code in emulation mode. Then like, for example, for the sake of simplicity, the same statement, let's say our program has only one statement, x is equal to y plus z. If TYP is integer, then addition, then the operation that happens on y plus z is y is an integer, z is an integer, you add y and z and you get x. If y and the z are floats, similarly y is float, z is float, add 2 floating point numbers, you get a float. And then, but if you make y as an interval type interval by making this TYP, and then we initialize the type of y to whatever it is, like let's say it is 0 to 255, and this is also 0 to 255. Then what happens is when we execute the program, x, the type of x, x is also of type interval. So the range for x will turn out to be whatever 450, 510, like this, it will turn out to be like this. And if you do affine arithmetic analysis, then what happens is, instead of this addition operation being interval operator, it becomes affine arithmetic operator. So the program analysis, it turns out to be fantastically simple using this approach. It's very, very, surprising. And we did it while investigating this problem, and we figured this approach, we found it very surprising and satisfying. I'll pause here and check if you have any questions. You're all doing all right? How many of you think this is a cool idea? You felt, wow, this looks cool. I felt really cool when when I looked at this solution approach for the first time. All right. So now, but the problem is what we did is we were not happy with, for some reason or other, we were not happy with generating HLS code. Or rather, we want to see how it will be like if we, instead of generating HLS code from the domain-specific language, Flowpix or Polymage, if we generate BlueSpec system Verilog code. So once we go to when we generate BlueSpec system Verilog code, all this program analysis that comes for free when we generate HLS code goes for a toss, and you have to work hard and write specific your own program analysis passes to get this range, to get these ranges. So yeah, and our interval affine arithmetic, while to some extent it can capture the dependencies between variables involved in a computation, but not quite thoroughly. Okay, but not quite thoroughly. So for example, if you see the image processing pipeline that we are seeing, this is what is called as an optical flow. That is the direction in which a car is moving, you can estimate by applying optical flow analysis. What it does is associated with every pixel in your image, given two images, for every pixel in the source image, it points out the direction in which that pixel is moving in the next image. Okay, so you don't try to understand. It has a combination of complex. It has a combination of stencil and point-wise stages. But what is important is if you see the dashed box, the dashed box is applied again and again and again. And as the number of iterations increase, the accuracy of the direction vector estimation also increases. Okay, this is how the Horn-Schunck optical flow estimation algorithm works. If you look at common X, like for example, so just follow what I'm my line of thinking or argument. So if you look at this common X stage, this is the common X stage. So there should be a line from here to here, I guess, which is missing. So common X stage is obtained, a pixel in the common X stage is obtained by dividing a pixel from IX stage with a pixel with a corresponding pixel from the denom stage. So if you kind of apply affine arithmetic or range analysis on this, it doesn't quite come out because you don't see any correlation between IX and denom. But then if you expand denom and write denom, then you will see that the denom is a function of IXX and IYY, and IXX and IYY are in turn functions of the stages IX and IY. So if you expand the computation, you can see that in the numerator IX is there, and the denominator also in the denominator IX square is there. So this critical relationship between this IX and the denominator and the numerator is lost. In the absence of that, the estimates that you get for the variables at the common X stage would be pretty bad. And this is what, and this bad effect, it compounds as the number of, remember, so here, this common X is being fed to common 0, and this is also fed to Vx0. So the whatever the mistakes that you make here, whatever, the bad estimates that you get here, when you keep iterating, as with the increase of iterations, the estimates keep on compounding, and you get a pretty bad estimates with the increase in the iterations. So for example, if you see, if you see here, with the increase in the iterations, so initially, so this column is if you use we use an SMT solver to solve this problem. We'll come to that later. But if you see here, this common X and common Y, they require 6 bits. The estimate of common X and common Y is 6 bits using interval analysis because correlations are not taken care of. But here we get 1 bit because correlations are taken into consideration. And then sorry. Yeah, like that, if you keep going from stage to stage. So here common 0, if you see, using interval analysis, it says no, it requires 21 bits. But the SMT solver based approach, which we will see in a while, it says it requires 14 bits. So again, common in the next stage, in stage 2, common 1 requires 33 bits. But according to interval analysis, SMT solver based approach, it says we only require 16 bits. But in any case, so what we are trying to say here is, so there is this particular approach which uses SMT solvers. Using the SMT solvers, we are able to get better estimates of bit widths at different stages. And this translates to massive amount of solving, massive savings, because if you see the last row, the bit width requirements of hardware stages, they are very high. If you use interval arithmetic, you might as well, you're better off using floating point numbers rather than using a 49-bit fixed point number. That too, it's just the integral part. But if you look at the corresponding SMT solver based approach, we just require 10 bits, 17 bits, 11 bits, so on and so forth. All right. So how this SMT solver based approach, I'll just give a brief intuition and then I will kind of stop there. So here what we do is we set up a system of constraints. So what is the system of constraints that we have? Common x is equal to ix divided by denom, because this is missing. And denom is equal to alpha square plus alpha is a constant, some 0.1 or something like that. Ixx plus iyy. And what is ixx? Ixx is equal to ix into ix. And what is iyy? Iyy is equal to iy into iy. And what are the constraints on ix and iy? Ix has a lower bound and an upper bound. And how do we get the upper bound and lower bound on ix? Because we know ix takes a input image whose where pixels come from this range, and we are applying a stencil operation. And when we apply stencil operation on pixels coming from this range, we know what will be the lower and upper bound. It's easy to estimate. So this LB1 and LB2, UB1 we can estimate. This LB2 and UB2 we can estimate using different approach. And we set a system of constraints. Okay. And once we have a system of constraints, what we do is we add one more constraint to this. Like for example, we add a constraint, common x is less than or equal to UB. So after adding this constraint, if the system of constraints is not solvable, then we know that the upper bound is not good. Okay, if it is solvable, then we how do we do the search here? So if there exists no common x with this, then we get a lower bound. So anyway, you get the idea. So what we do is we look for this system of the first set of constraints, they remain the same. And what we do is we keep tightening the range of common x, the lower bound and upper bound for common x, by repeatedly by using a binary search. So we add a bound and we add that constraint to the system and use it as SMT solver. The SMT solver that we use is what is called as a Z3 solver. It is from Microsoft Research. It's a very good solver. And that solver will tell us whether the system is solvable or not. And if it is solvable, then we kind of adjust our upper bound or lower bound, and then again continue our search process. So this is the plan, and I'll quickly summarize the results. More than the strategy is very cool and interesting. There is one more thing. So we figured out how to use alpha, that is how to find out alpha. We can, in order to find out alpha, you can use either interval analysis or affine analysis. They have some limitations, and we can use SMT analysis. But in many cases, interval and affine analysis may just be fine. So you don't need to sweat it out. After you find it, you want to search for how many fractional bits are required, whether 1 is enough, 4 is enough, 3 is enough. We need to find it out. So here we just do a greedy search by running the pipelines on few example images and see how things pan out. Okay, whether they are good enough or bad. So what we do is, like, for example, if you look at the Harris corner HCD, so if you take the HCD stage, so let's say this is, if you kind of order them in, this is the topological list. If there are 10 stages, this is the topologically sorted list of stages. We go to stage S10 and we will initially start with, let's say all the stages require 16 bits of fractional representation. So we start here and we keep dropping. Instead of using 16 bits for fractional representation, we use 15 bits and see if the results are still satisfactory. And as long as the results are satisfactory, we keep dropping the number of bits allocated to the fractional part. And after S10 is fixed, we move to S9 and then again repeat the same process. We try to reduce the number of bits allocated to the fractional bits. And as long as the accuracy is to our satisfaction, we keep dropping. At some point when the accuracy takes a hit, we retain that number. So this is the plan for finding out the number of fractional bits. This is a simple greedy algorithm. But in literature, you will find very, very complicated algorithms to solve this problem. But we took a simple approach. So based on this, if you see the last column tells us how many fractional bits are required for at each of these stages. Okay. And yeah, let's look at this. HCD is what we are looking at. In the case of HCD, you really don't get much benefit. But if you look at optical flow, this is where is optical flow? Optical flow, we have already seen that by using this particular approach, how in the optical flow, we are able to accurately estimate the bits required at different stages, both the integral bits and the fractional bits. So now let's finally, at the end of all this exercise, all this effort should translate to some savings for us, right? So if you see the optical flow, the data associated with optical flow, if you just use float data type, then the number of FPGA slices used, this tells the amount of area that we are using, is 65%. And the throughput is 171 megapixels per second. And we are, the flip-flops required is some 33,000 flip-flops. And the DSPs required are 168. BRAM tiles are required 34. And then of course there's the power consumption, 0.614641 watts. But if you use the SMT solver based approach, then you can see that there's a reduction in the power savings. We are able to save power well. And the BRAM tiles, we are using close to 50% less BRAM tiles. And the number of DSPs required reduced from 168 to 22, and flip-flops reduced substantially. LU2 usage also reduced more than 50%. And same is the case with FPGA slices and the throughput, while at the same time, we are able to increase the throughput because we are able to save on the latencies, etc. And we are able to run we will be able to run the whole design at a higher clock frequency also. So the moral of the story is when you are working, on hardware designs, it's important that you pay attention to what is your data type. Do you want to use a float data type? You want to use a double data type? You want to use a fixed point data type? If you want to use a fixed point data type, whether it should be the same for all the variables, whether you want to use different fixed point data types for different variables. And And then, and all these things will have an impact on the BRAM slices used, the memory bandwidth, that is the stress on the memory bandwidth, DSPs used, flip-flops, everything will have an impact on this. And this you will not, this particular thing you will not be able to make use of in CPUs and GPUs quite well, because there the granularity of the data types are small. They are very coarse grained. Like a float, double, I think these days 16-bit floating point numbers are also introduced, I guess. If I don't know, perhaps given all the things stuff in the deep learning space, maybe 8-bit floating point numbers might also have been introduced in GPUs or in CPUs. I'm not sure about CPUs though, but perhaps in GPUs they may have something like that. But in FPGAs, we have a whole lot of flexibility. And when you are looking out for performance, this is an important dimension that you need to consider. And usually when you look at a paper, you look at two papers, and one paper may kind of report twice the performance as the other paper. So you should not immediately conclude that the other paper is better performing, because if you go look into the details, one paper, the paper which is performing low, it could be using floating point data type, and the other paper could be using fixed point data type. And while using fixed point data type, it is not guaranteed that you'll always get the required accuracy. So, but hopefully that is the case. So, so that's what we should look for. So if you are able to, while moving from floating point to fixed point, if your accuracy is reducing from 99% to 97% or 95%, and if the application demands, and if your application is fine with 95% accuracy, then you might as well go with fixed point data type and get all the benefits that you get from it. Okay. So keep this in mind, and as a whole, many interesting ideas are covered in today's class. I will conclude here. The summary of today's lecture is how DSLs could be useful in raising the level of abstraction one level more. And number two is, how program analysis techniques can help you in figuring out some important information about your program. Especially in this session, it's about estimating the required data types at different stages in an image processing pipeline. And if you choose these data types appropriately, then it can have a big impact on your application performance. Yeah.
Sir, here the project of this course, are we going to do it on HLS or DSL?
HLS. Yeah, you are doing it on HLS.
Okay.
Yeah, you see, you are the people who should be learning, become HLS masters, and build DSLs for others. Okay, it's your job is not to use DSLs.
Okay. And sir, as sir, the eLearn site is down, so we are not able to access the materials from there.
Oh, is it? Okay.
If you can find any other.
Yeah, okay. I have this. Everything is on. I will send the links. Everything is on YouTube. I just have to share the links. I thought eLearn is up, so.
Yeah, sure. It's down for past 2 days, I think.